then you can prove that even though each bit is mathematically well defined, well determined once you pick the programming language, it looks like a perfect simulation of independent toss of a fair coin.
There are also statistical mechanics definitions of randomness by Martin-Delgado and this type of...
Well, this definition is not... This is... Yeah. There's the kind of definition that Kolmogorov and I were using to define lawlessness, which is algorithmic incompressibility. And Martin-Delgado was using initially the proposals used the 1960s version of program size complexity. And there's a problem, which is the natural definition of defining randomness as incompressibility with that version of program size complexity doesn't work for infinite sequences. And therefore, Martin-Delgado said, let's save this proposal that he had learned from Kolmogorov, that I had made independently in the US at about the same time. He said, let's save it by dropping Kolmogorov's idea of looking at the size of computer programs and having this notion of information, and let's save it by just defining an infinite random sequence of bits, or a random real number, as one which satisfies all possible statistical tests of randomness. So he proposed a definition, a sort of a statistical version of a random infinite sequence, or of a random real number. And then, but I didn't give up. Kolmogorov was incredibly old when all this was happening. He was my age, and he basically handed the field to his students. But I kept going. So in the 1970s, I and independently Levin said the definitions in the theory are wrong. You need to use self-limiting programs for a number of reasons. And one of the reasons that I switched to change the definition is because once you do that, then the original intuition that Kolmogorov and I both had independently is that you can define a random infinite sequence as an incompressible one works. So the way you can prove that it works is to say that it turns out that an algorithmically incompressible infinite sequence of bits turns out to satisfy all statistical tests of randomness, which is Martin-Delgado's definition of a random infinite sequence, which uses actually constructive measure theory is what it's really using.
So they are equivalent in the case of infinite.
They're equivalent in the case of infinite, right. With finite, it was clear that this works. It gives you, depending on whether you use the 1960s version or the 1970s version of this theory, you get a slightly different set of... actually, the most random sequences turn out to be the same. It doesn't matter for finite sequences. It doesn't matter which theory you use. But some delicate properties having to do with sequences which are not the most, finite sequences which are not the most random possible, it turns out it's different. When you ask how random something is, a finite sequence is, depending on these two definitions, you get different answers. And you get better answers with the 1970s version of the theory. So in the 1970s, the whole thing fell into place. And one of the ways to say that it fell into place is to say that the definition of an infinite random sequence is one where for every finite initial segment, it's incompressible. The smallest program that calculates it has to be about the same size. That turns out to be equivalent to a sort of a natural statistical notion of randomness, which Martin-Delgado defined using constructive measure theory. It means, I don't know if people are interested, his notion was saying that a sequence is random or a real number is random if it satisfies all possible statistical tests of randomness, but it had to be an algorithmic statistical test of randomness. So basically what that is, it's a random real number cannot be contained in any set of measure 0, but there is no covering, but it has to be a covering which is algorithmic. That's why you're using constructive measure theory. Because you see, any individual real number can be covered by a covering which is not algorithmic, so then there would be, nothing would be random. So in other words, the way you see that most strings are random, you have to restrict yourself to only allowing something is random if it's of measure 0, where the covering has to be as small as possible, but there has to be an algorithm saying you want to cover this real number with a covering which can be size epsilon, where epsilon can be as small as you want. So basically a covering in constructive measure theory that Martin-Delgado used is an algorithm where you say how small you want the covering to be, and it will find a infinite set of intervals in the unit interval which include the real number you're interested in and which can be as small as you like, that covering. So that's this notion of a set of measure zero. So that's a statistical test of randomness. And since it turns out that there are only a denumerable infinity of such randomness tests, the total measure of the stuff which is counted as non-random is going to be zero. So the total measure of the stuff that is random according to this definition is unity. In other words, almost all infinite sequences are lawless. For finite sequences, most finite sequences of n bits cannot be compressed in programs smaller than they are because there aren't enough small programs. There are 2 to the n possible n bit programs, and there are 2 to the n possible n bit sequences. And if the programs have to be much smaller than the sequences, there cannot be enough theories to explain that many sets of observation. And in the infinite case, the way it becomes that with the set of non-random infinite sequences turns out to have 0 probability. So if you pick a real number at random in the unit interval, with probability 1 it's going to be algorithmically incompressible, and it's also going to be Martin-Delgado random. And those of us in the field were happy when it was possible to prove that these different definitions were equivalent. And there's another definition, the first statistical definition of a random infinite sequence was due to Martin-Delgado, but there's another definition due to Sala de, which is technically better than the Martin-Delgado definition, and they're equivalent. So there are basically 3 different ways of defining a random infinite sequence, and it turns out that they're all provably equivalent.
But for finite sequences, only the algorithmic version works.
Right. There is no statistical definition of right. And the right one to use, in my opinion, is the 1970s version, because then you don't want then that same, because with that definition, you saying that an infinite sequence of bits is incompressible or irreducible, that the first n bits always requires a program that is greater than n minus c bits to calculate it, that turns out to be equivalent to statistical randomness. So in other words, using these ideas, you can prove that this number looks normal in Borel's sense, that the zeros and ones will happen exactly 50% of the time. In other words, you can make very strong statistical statements about these bits, the same way that happens in quantum mechanics, where you can't prove what will happen in an individual case, but you can calculate probabilities. So you can prove that the 0 bit will, in the limit, happen exactly 50% of the time in this binary expansion. And the 1 bit, of course, will be the other 50% of the time. But if you look at 2 bits at a time, you can show that each of the 4 possibilities will happen in the limit exactly 1/4 of the time. If you look at 3 bits at a time, you can prove that each of those possible blocks will, in the limit, happen exactly 1/8 of the time. And the same if you write this number not in binary, but in base 10. So this is a notion that Emile Borel talked about a century ago of a normal number, and it's one where if you write it in any base, the digits and all possible blocks of digits will be equidistributed. And he proved a beautiful theorem saying that most real numbers are normal in every base, which means that not only does every digit have the same limiting relative frequency, but every block of digits does also. And he proved that with probability 1, this is the case, but there were no natural examples of a real number with this property, even though, so this is the first natural example of, comes. So this is how randomness, now, I'm delighted that this is a physics department. I don't know if most of you are physicists or what, but physicists tend to like these ideas, and pure mathematicians tend to either not understand or hate them. Because this notion of randomness in theoretical physics has a tremendous tradition, right? Going back to statistical physics, Boltzmann mechanics, and in quantum mechanics, right? And we've learned to love randomness in theoretical physics. But the notion that there's randomness in pure mathematics, and that there are limits to the power of mathematical theories, which are basically thermodynamical limits. This notion of program types complexity is like an algorithmic version of entropy. It's the entropy for individual sequences. You know, there are no ensembles here. This is a notion of entropy that applies to individual microstates. And these notions are very natural for those of us who love physics. But in the world of logicians hate this stuff. You know, to them this is madness. You know, randomness in pure mathematics, you know, that's, logicians are people who can't cope with randomness. That's why they became logicians. They like to think everything is black or white. Either it's absolute truth or it's absolutely false. So physics, I've gotten more invitations over my life to talk about these ideas to physicists than to pure mathematicians, and logicians never. So, because this is an invasion of ideas really coming from physics, I would say, into mathematical logic, and obviously people don't feel very uncomfortable. It's not just for political reasons, because it's outsiders, you know, going into your field. It's also because these ideas really are incomprehensible to logicians and to many pure mathematicians. Not in the old days. In the old days, pure mathematicians would also know theoretical physics. Hermann Weyl is an example of that, John von Neumann. But nowadays, so I wanted to be a physicist when I was a student, so that's why I got corrupted by ideas from physics, right? Okay, so this is a sort of a even better example that pure mathematics has infinite complexity and is more biological than biology. Because right here, every one of these bits is one irreducible bit of complexity, you see, of mathematics.